Testing, testing. Okay, today's lecture is on distribution of primes, so I'll go through some details of some very classical simple theorems in elementary number theory on the distribution asymptotically of prime numbers. This lecture was motivated by an email that was sent around the department very recently. And it was coincidentally it was on April 1, so there was some thought that this might be an April Fool's joke, but I did some searching on the web. But this is the press release saying that in a sort of breakthrough in this area of number theory, two mathematicians, Dan Goldstein of San Jose State, California, and also Cem Yildirim of Bogazi University in Istanbul, forgive my pronunciation. These two researchers have much sharper results on the distribution of primes for large numbers. There's something called the twin primes conjecture, which says that there are an infinite number of primes which differ by 2. So obviously a prime can't be even, so the closest two primes can be is differing by 2. So for example, the pair 101, 103, 107, 109 are pairs of twin primes. A very famous $1 million open conjecture is that there are an infinite number of twin primes. And some people know a little bit about the format of these. For example, all of them except for one are of the form 6n plus or minus 1. I believe that doesn't look like it's true, but there's some results that give the format of these, but nothing really much is known about the distribution of pairs of primes as n gets large. In particular, what the natural distribution of primes is. Now, it is known that on the average, if n's a prime number, then the difference between that prime and the next prime will be, on average, something like the log of n. So the primes tend to get further apart, but that's only on average. So on any interval of log n, the question is how many extra primes could be in that interval. And a very famous result dating back to 65, Enrico Bombieri said that there are at least half the primes, well, there's an infinite number of primes of gaps that are less than half the average size, log n. So in other words, the difference between primes is less than 1/2 log n. So here's a list of links that I've put together just on the background. I had found a link to this fellow's homepage, and here he is relaxing at home with his kids. So it gives a little bit about his fall courses, mathematical interests, publications and preprints. There's a really nice link to the server here, Mathematics Archive. If you click on that, you can actually get preprints on the web. So for example, if I put in as an author Goldstein and title something to do with primes and click on listings, oops, no, it matches, so let's just cut out that. Okay, so it gives you 3 abstracts that it found. Now this particular archive has archived, I don't know, something like 30 or 40,000 papers. So if you click on these, you can get it as a PS file or a PDF file. So if you click, say, on the PDF file here, it will bring up the actual paper. And it brands it so that you can't print it off without acknowledgement. So this is, I believe, only papers from 1992 on, but it's an excellent source of, yeah, here we go. So this is a preprint, higher correlations of divisor sums related to primes, K correlations by Goldstein and Yildirim. This is a third in a sequence of papers. The first and third are on this, not the second for some reason, but you could probably find it on the web. Okay, so that's his website. He's a research mathematician at San Jose, as I said, who has worked all his life on prime numbers. Also, there's a press release from the American Institute of Mathematics, which is a great title. San Jose State math researcher experiences epiphany at American Institute of Mathematics. Epiphany is like a religious experience where the lights come on and you have eureka and everything kind of clicks. And it doesn't happen very often, I can testify to that. But it claims that this fellow, Dan Goldstein, was standing in front of a whiteboard at this Institute of Mathematics when a comment made by a fellow mathematician sparked a brainwave, as it says, and that inspiration enabled him to devise a completely new approach to something he'd been working on for 20 years, and then he's presenting this culmination of 20 years of research later on in April. So it's this paper entitled Small Gaps Between Primes apparently has this. Normally in mathematics, when you have estimates on prime numbers, you sort of move the constants from 0.5 to 0.48 to 0.47, and you kind of chip away at it. He basically got the constants down to 0 in a certain sense. So this, again, outlines sort of what the problem is, namely the frequency of twin primes decreases, but do they ever end after a certain point, or is there always, for any number n, can you find a pair of twin primes greater than or equal to n? So he's presenting this at a conference in algorithmic number theory. There's a more technical summary of the details of the results here. So if you let the prime numbers, sequence of prime numbers, suppose you let Pn be a prime and Pn plus 1 be the next prime. There is no formula, by the way, that is a polynomial formula such that if you plug it in, then its value for integers is always going to be a prime. Many people looked for many years to find a formula that would guarantee you that you could generate a prime by plugging in an integer. And then someone very recently, I'd say 40 years ago, showed that there is no polynomial of finite degree that will generate a prime, at least in one variable. I think there's also a result that says as a polynomial of 26 variables with basically very hard to determine constants, you can find a prime generating, but it costs you longer to evaluate the polynomial than to check if something is prime or not. So the conjecture, the Goldbach conjecture, says that Pn plus 1 minus Pn number equals 2 infinitely often. So let me just illustrate. I mean, this is something you've seen probably back from high school, if not earlier. There is the most ancient way of finding primes is the sieve of Eratosthenes. And most of you, I don't think I spelled that right, but it's close. And what you do is you just label the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. And then what you do is you take off all the multiples, say, of 2. So you remember, a prime cannot be divisible by any number besides itself and 1, etc. And then you take off all the multiples of 3, 6, 9, 12. Take off the multiples of, oops. Well, yeah, you do this and you're not going to end up with any prime. Okay. You leave that.
We now have one as a prime number, and that's it.
Okay, you're correct. This is not, I should not scratch off the first one. Okay, so 5 you leave alone, and you knock off 10, 15. 7 you leave alone, and you knock off 14. So the numbers that are left, the first occurrence, these are going to be prime numbers. So the sieve of Eratosthenes is actually a way of generating lists of primes. But if you have a very large number, say 512 digits, it's going to take you a while to cross off, you know. If you have a prime number that's like 10 to the 512 digits long, I mean, it's going to take a huge amount of time for the sieve to get up to that number. So this is not practical. So the question is, and there's no closed form formula. There is no closed formula to generate primes. No, most of the computer algorithms will tell you if a number is prime or not, but it won't generate. Like there's nothing known that will say, give me the 2,470,653rd prime, other than a table lookup, which means you've already done the calculation. But you can't find a formula f of x so that when you put in x equals 2,570,463 that you get that number prime. There is no such formula. So, and that brings up an interesting question. There are three fundamental questions. So question one is, is there a formula to generate primes by a formula? And the answer is no. No, there is no polynomial formula. That's proven, or at least of a single variable. As I mentioned, there are some highly multidimensional formulas that seem to generate primes, but again, they're more complicated. Okay, and they're not really useful. So the second question is how can you tell, well, the problem is factoring an arbitrary number, a large integer. Now obviously, one method is to just try, if you're going to factor n, you can look at the factors 1, 2, 3, 4, up to square root of n, because after all, factors appear in pairs, so if you have something less than the square root of n, then there's a number greater than the square root of n, so you only have to find the first root n integers. But this basically is not very efficient, because 10 to the 512, you can't list the integers in time less than the known lifetime of the universe. You can't list the numbers. So factoring large integers by checking divisors is not practical. So checking divisors is not practical. But there's a third question, and table lookups only are useful for small primes. So the question, the most interesting remaining question is, can you determine whether a number is a prime without finding its divisors? Can you check if n is a prime without factoring it, without knowing its factors? And that's the basis of all these RSA encryption algorithms. They rely on the complexity, the difficulty of factoring a prime, along with the relative simplicity of checking with a high probability whether a number is a prime or not, but without giving you its factors. So you plug in a number n, and it might say, okay, it may be a prime, it may not, or you can most often say it definitely isn't a prime. But even if you know it's definitely not a prime, it doesn't say what the factorization is. Okay. So, what's known about the so-called gaps? Well, if you look at, if p sub n is the nth prime, and p sub n plus 1 is the n plus first prime, you can actually plot the gaps. And in fact, there is a link here on prime gaps, and it gives a of what the function looks like. excuse me, it's not that length. That is on prime gaps, but it's the prime difference function. Okay, yeah, here's a picture of the gaps as a function of n. So in other words, if you plot the difference between successive primes, n and n plus 1th prime, as a function of n, this is what the function looks like. Now that's rather a nasty function. It looks just like noise. And in fact, there may be some underlying statistical distributions of this function. And in fact, one of the papers of Goldstein relates essentially the Poisson distribution properties of this distribution. But it's not a known, precise statistical distribution. But there is an inequality that says that the gap b sub n between two successive primes is bigger than some constant times log n, log n, and log n divided by log n squared. Okay, that's obvious to everyone, right? For infinitely many n, not for all n, but for infinitely many n, and for some constant that's in principle computable. Now, this actually, this math world actually picked up this Goldstein result in 2003 because this is his result. This says that the lim inf of the difference of primes divided by the log is equal to 0. Now, what does that mean? Well, if you take Pn plus 1 and you look at Pn and you look at log n, and then you look at this number, you want to say, is this bounded? Is this less than some constant? And the answer is yes. As you go and you look at the limit of this, you can actually show the first estimate was that it was less than 1. And, right. So the first estimate that it was less than 1. And then Hardy and Littlewood, very famous mathematicians, got it down to 2/3. Then Rankin, assuming the generalized Riemann hypothesis, got it down to 0.6 from 0.66, assuming the generalized Riemann. Erdős, who's a very famous mathematician, gave a proof without those conditions that was less than 1. Bombieri got the most sharpest estimate in 1966, where he got it down to 1/2 without any. And then using the generalized, we got it down to 0.46650, then to 0.44254, and then to 0.2486, which was the best result until now. Now, the best result till now is that Goldstein and Yildirim got this inequality. So Goldstein just recently proved this inequality, that Pn plus 1 minus Pn is less than 1 times the log of Pn to the 8/9. So log of Pn to the 8/9. Now, if you divide through by the log of n, what does this imply? That Pn minus 1 divided by Pn divided by log Pn is less than log Pn to the what? 8/9 minus 1 is negative 1/9. And that goes to 0. So that certainly beats out 2.486. So in fact, this goes to 0. Now, that just says that the distribution of primes, Pn minus 1, is less than some constant times log of Pn raised to some alpha, where alpha is less than 1. Now, unfortunately, the difference in primes, this number goes to infinity, because the log of the Pn, after all, goes to infinity. So this number can be, this just says that you cannot bound the gaps between two primes. So the gap between primes, gaps can go to infinity. And in fact, you can easily show that there are sequences of composite numbers, that is, numbers which are not prime, sequences which are arbitrarily big. So this is reasonable. So the claim is that the gap between primes gets larger, possibly, as the prime numbers get larger. Now, I'm going to actually construct a series of numbers. I'm going to construct a number n plus 1, up to n plus n, where all of these are there are no primes in this gap. That means the gap is equal to n. I'm going to give you an actual construction, and it's obvious that every number, n plus 1, n plus 2, n plus 3, up to n plus n, is not a prime, because I'll show you its factorization. And it's actually an elementary proof. It's pretty obvious once you look at it. Just let n be n factorial. Okay? Now look at the number n plus 2. That's n factorial plus 2. Well, that's 1 times 2 times 3 times 4, all the way up to n plus 2, right? Now factor out the 2. So factor out the 2 here and here. It's 1 times 3 times 4, all the way up to n, plus 1. This is an integer, that's an integer, and so you showed n plus 2 has 2 as a factor, right? Same works for n plus 3. n plus 3 is n factorial plus 3. It's 1 times 2 times 3, etc., plus 3. So you factor out a 3, and it's 1 times 2 times 4, all the way up to n, plus 1. 3 is an integer, n is an integer. In fact, you can go all the way down to n plus little n. So it's 1 times 2 times 3, all the way up to n plus n. So obviously n's a factor. 1 times 2 times 3 times plus 1. So n plus 2, n plus 3, all the way up to n plus n. And there are, of course, n minus 1 of these. There are n minus 1 of these which are composite, non-primes. So that means the gap between these two primes has to be at least as big as n. So you can always find gaps which are arbitrarily big. So you cannot ever prove that the difference between successive primes is bounded by a constant. That's false. So Pn plus 1 minus Pn bounded by some number big is false. M has to go to infinity. Okay, so I'll make sure that that's false. Okay, so what is true? Well, Pn minus plus 1 minus Pn must go to infinity, but the question is how fast does it go to infinity? Well, the earlier results said that it went to infinity like a bounded constant times log n, and Goldson actually gets it to be log to some power less than 1, which is better. It goes to infinity. Now, this doesn't say that 2 is the smallest difference between primes, and 2 is obviously less than infinity, so the question is how many primes have the minimum gap? And that's an open problem. You solve that, you get $1 million. Okay, so a little bit more about, okay, and actually they've shown that the gap of length r obeys this estimate. Okay, so actually it made the BBC article. So they announced this. That's how I knew that was not an April Fool's joke, because BBC would never report an April Fool's joke, right? So we'll skip the BBC article. It seemed to hang up my browser. So the prime gaps is something we've talked about previously. This gives a lower bound on the gaps in terms of this combination of log, 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 4 logs divided by 3 log n for an infinite number of constants. And then this new result of Goldstone presented over Wolflock substantially sharpens that. And they got the number 8/9, and this actually reports 4/5. Now there are some results. For example, if you let p of n be a function that gives the first time the prime with where the gap of n first appears is approximately like exponential root n. It's probably something like a factorial. And then there's some other things on the prime gaps and twin primes, etc. So I found a paper here, Hardy's contribution to number theory. This is a PDF paper that's a very nice kind of survey, 30-page survey of G.H. Hardy's and Littlewoods and Ramanujan and other people's legacy in the area of prime numbers. Hardy was a giant of pure mathematics, and this is an article by Vaughan that sort of gives a summary of that. Okay. I'll let you read this on your own. There's also another paper which I tracked down by a Polish mathematician, Marek Wolf, which is on the first occurrence of a given gap between consecutive primes where they get estimates. You can see the estimates here. Square root of d exponential, the square root of log n squared d plus 4d. A lot of asymptotics and goes into this. There's also a nice survey article on twin primes giving an estimate that is bounded above by 100x over log x squared. And that's the number of numbers with 2 factors. And then there's some further estimates. And this one doesn't have Goldstone's estimate for this in it. Now, one of the very famous results of number theory is the following. It's the prime number theorem. And that is if you look at pi sub n, which is the counting function, pi n is just the number of primes less than n. So if you were to just make a little survey, define a function pi of n, so that's the number of primes less than or equal to n. So this has a value for n, and for example, if there are no primes in a gap, that just means pi is constant. So what happens is you get primes and then primes, then it goes up like this, and then it may have a gap and go up like this. So it's definitely not a smooth function. But there is a function that it approximates called L sub I of x. So in fact, the prime number function is like L sub I of x, and L sub I of x is something called the logarithmic integral function. And for that to be defined, I have to go back to the previous one. The logarithmic integral is a definite integral, which is the integral from 0 to x dt over log t. So that's integral from 0 to x dt over natural log of t. Okay, so that is, this has a weak integral singularity at 0, and if you normalize it so that pi of 1 is, I believe, 1, or pi of 2 is known, you get this following result. If you graph the distribution of primes, then it looks, here in red is the actual distribution of primes, and in black is this function, logarithmic integral of n. Now, many people, like Legendre had a guess at this. Gauss actually just looked at tables of primes, and he actually just by observation said, gee, looks like n over log n. And he may have just fit that function or did least squares or whatever. Actually, n over log n is the first term in the expansion of the logarithmic integral. And the logarithmic integral is a better distribution. Now, it looks like this is an upper bound, but in fact, you can show that these two curves cross, that eventually the prime numbers will equal and then exceed the logarithmic integral of x. And in fact, someone showed that the first crossing of pi and this logarithmic integral occurs before 10 to the 10 to the 10 to the 34th, which is an enormously huge number. I mean, it's bigger than a Googleplex, which is the biggest number that has a name. Well, this has a name and it's bigger, so I guess that's not right. Now, there are, in fact, limits on this ratio. Chebyshev, and you'll recognize that name, Russian mathematician, actually said that the ratio of the prime counting number to this rough estimate, n over log n, that is bounded between 7/8 and 9/8. So it can cross, namely can equal 1, but it can't get very much bigger or much less than it. So it's trapped. So you can always count the number of primes. In fact, if you look at that, what that says is that pi of n is less than 9/8 and bigger than 7/8 times n over log n. N over log n. So this actually gives you an upper and a lower bound on the number of primes that are less than n. So if you want to know the number of primes that are less than 10 to the 30th, this will give you, not very sharp, but it'll give you estimates. Okay, that's kind of nice. You know, that when they first wrote down this graph, they said, boy, that looks smooth. Because most people were expecting a graph that looks like this. Something really, really noisy in the distribution, just wandering all over the map. Okay, I've tracked down 3 different proofs of the prime number theorem. Now, I'm not going to do that in class because it would probably take the better part of an elementary number theory course to go through the proof of the prime number theorem, but it was a proof by using Fourier transforms. This is a LaTeX to HTML. There's a proof given sort of as an outline, more or less a heuristic justification. It said that the prime number theorem was noticed empirically by Gauss when he was a teenager, after he was studying lists of prime numbers in his spare time. There's always a good reason why you should look at tables of logarithms and stuff. You never know when it'll come in handy. Here's another nice survey on prime number theorems, comes from Harvard, and it ties it very intimately into the Riemann zeta function. And then there's some results on the prime counting theorem, and that's, again, this factor here. And so in fact these are lists of people who counted primes up to 10 to the nth. So all the primes up to 10,000 were known in antiquity. Primes up to 10 to the 25th, gosh, was known in 12,002. I guess the number of, hold it, this didn't look right. So the following table gives the values of pi n for powers of 10. Oh, okay. I guess someone had counted the number of primes up to 10 to the 25th. That seems pretty hard. Unless they just counted them by, yeah, I don't know what that exactly means, but people have been looking at it for a long time. Now, there's a result called Fermat's Little Theorem, which I'll state down here, and I'll study, and I'll do that in, and anything with the name Fermat, and you should pay attention to. So this is known as his little theorem, because his big theorem is the one that was just proved, x to the n plus y to the n equals e to the n. So this is not his last theorem. It's not his big theorem even. It's just Fermat's little theorem. But it actually is not so little because it underlies many of the modern encryption theorems. It just says, and I'll state this as a theorem, if p is prime, if the number p is prime, and the number a is less than p, and, well, then, I should say, there's no more ands, then a to the p equals a mod p. So this says, in particular, if p is a prime, pick any number less than p. This says if you divide p into ap, you'll be left with remainder a, if p is a prime for any number. Now, I'll show you how to prove this in a few lines, but the consequence is very important. If you pick a number, if a is less than p, and AP does not equal A mod P, then P is not a prime. So if you pick a number A and you pick a number P and you compute A to the P power, and you can do that on a computer pretty fast, and you look at what the remainder is, mod P, if it's not equal to A, then P is not a prime. So this is a test to see whether P is a prime or not. Now, notice this says for all A, so you'd have to check for all A. But in addition, but only one is needed for the converse. So if you can find a number A that's less than P, so that this is not true, AP does not equal to A mod P, then P is not a prime. So if you just guess numbers, plug them in and check, the first time this fails, it's not a prime. So it's a way of verifying whether a number is a prime or not without factoring. Now suppose you go through every number A up to P, and this is true. AP is equal to A mod P. Does that guarantee that P is prime? In other words, is the converse true? No, otherwise it would be an if and only if, right? So it's not. There are numbers, P, which are not prime, which satisfy this, and they are called pseudoprimes. So that's the problem. So the problem is there are numbers, P, which are not prime, which have the property a to the p equals a mod p for all a less than p. These are called pseudoprimes. They're there in the universe just to mess your algorithms up. There are not many pseudoprimes. In fact, you can count the number of pseudoprimes, and statistically, they're almost insignificant. Pardon? 531 is the smallest. So p equals 531 is the smallest pseudoprime. Now, you can actually prove this, and I'll probably do that on Thursday, because I do have a nice little proof. There's another statement of it. There is an if and only if called Wilson's. It says, let p be an integer bigger than 1. P is a prime if and only if p minus 1 factorial is equal to minus 1 mod p. So Wilson's theorem says that p is a prime if and only if p minus 1 factorial equals minus 1 mod p. And what that means, of course, is that p minus 1 factorial is some constant k times p minus 1. So p divides p minus 1 factorial k times, where k is an integer, with remainder minus 1. Okay? So, you might say, gee, if I put in a prime p, all I have to do is calculate this number and see whether I get minus 1 mod p. Well, put in 100. Is 100 prime? Well, you'd have to see, is 99 factorial equal minus 1 mod 100? Well, unless you've got really fast ways to do modular arithmetic, you've got to compute 99 factorial, and that's just for prime 100. If you're doing primes with 10,000 or more, you have to compute 10,000 factorial. And the amount of cost, n factorial, is a huge number. In fact, by a formula called Stirling's formula, n factorial is what's like n to the nth. Let's see if I can write down the exact asymptotics. I put it down here. Yes. Stirling's formula says that n factorial is roughly root 2 pi n raised to the n plus 1/2 power e to the minus n. But what's really bad is this n to the n in here. That means 100 factorial is like 100 raised to the 100th power, and it's just enormous. Even with this e to the minus 1/2. This is big. N factorial gets big very, very fast. It gets big faster than even exponential. It's worse than exponential growth. So that's why it's a beautiful result, but mainly theoretical, because you can't compute p minus 1 factorial unless p is less than 100, and you know the first prime's up to 100, so it's not too useful. Pardon? No, it doesn't. It's just a theoretical result. It's an if and only if, rather than Formas. Formas' little theorem does tie directly into encryption, because one of the fast ways of, well, if you can determine whether a number is prime or not, that's one of the ingredients in the RSA. You have to factor and you have to determine whether a number is prime or not. So, in fact, if you want to go look at this, that's one of the lectures of the, let's see, I think it was on the previous one, the RSA encryption, factoring primes there. So this Fermat's little theorem is embedded back down in here. or maybe it's the DSS algorithm. Somewhere it's in the maybe it's in lecture 20. I know I had it. Yeah, DSS algorithm, and I think it's down somewhere in the all this modular arithmetic. If we look for Formas, I'm sure he's in there. Yeah, here we go. By Formas' little theorem, you've got some results. So Formas' little theorem is buried in DSS algorithm, which is the NIST standard, and that is part of today's certificate encryption standard. So that's where it ties in. However, that's somebody's final project, I hope, will do this. Okay, so I will do the proof of Fermat's little theorem in the next lecture. It'll probably take 10 minutes. Actually, it just needs the binomial expansion, that's all. It's an induction proof, so I'll write that down. And then we'll talk a little bit more if there's another sort of current problem